Dear guys, Assalamu alaikum. My name's Mohammad Gyashuddin. In fact, I'm physics teacher of my own school, Gypsy. Guys, now I'll discuss differential equation of simple harmonic motion. Okay, what is that equation? That equation is d squared x dt squared plus omega squared x equal to 0. This equation we have to derive. Guys, how can we deduct this? We have to know the way of deduction. Okay, fine. Guys, here we can see x omega t. That means we need a particle. Actually, at first you have to know simple harmonic motion. What do you mean by simple harmonic motion? Guys, if you know the pendulum, then you can understand the simple harmonic motion. Okay, let me describe this. Suppose this is a string and there is a ball. And if you draw this along the side and release, it will come here, again it will go there. Such way it will vibrate, it will in motion. Okay, it will be this type of motion we could say simple harmonic motion. Okay, and due to this motion there is some condition. Since this ball has gone this point, that's why it tries to come back to this point. Okay, so we can say some words here. Restoring force. If okay, we could say acceleration, or we could say displacement. Guys, these three words we have to know. Anyway, through the direction of this differential equation of simple harmonic motion, we may understand. Guys, later there is a particle which is in motion of a simple harmonic motion. Guys, that particle mass m left. Okay, and at time or after time t, it has displaced x distance. Guys, suppose a particle is in such motion, simple harmonic motion. So a particle goes to this point, comes this point, again goes to this point, comes to this point, again goes to this actually simple harmonic motion because there is some condition which the particle will abide by. Okay, guys, we've taken a particle whose mass is m, and at time t, it has displaced x distance. Yeah, suppose from here, from the midpoint, it has gone x distance, suppose here, at the time t. Then we can say there is a velocity of the particle. Okay, the velocity v equal to dx over dt. Guys, this is the velocity of the particle because it has gone the displacement x. Suppose this distance it has gone x. Okay, the time t and is the mass of that object. Guys, it's very important because just now we have known the displacement and we have known the time and we have known the mass of the particle and we've got the velocity dx upon dt. Since we've got velocity, that's why we could say what is that? Acceleration. Very simple, guys. Acceleration here of this particle. Acceleration means dv dt, right? So d dt and v means here dx dt. Okay, just now we got this. Okay, so d square x upon dt square. This is the acceleration. Guys, we've got velocity and acceleration. Now, from the simple harmonic motion condition, we can say, what can we say? Anyway, forget about that. We know the Newton second law. Actually, here we'll apply the Newton second law. Guys, the particle is in motion. Guys, how it has got the motion? Due to force. Guys, due to force, this particle has got motion. Okay, that's why we could say, what can we say? We can say the force. Just so you have known the mass of the particle m, and we have produced the acceleration a. That's what we can say. If equal to ma. Okay, and if you m and here d squared x upon dt squared. This is F equal to m. And now, on condition, due to simple harmonic motion. What is the condition? Actually, this particle has gone to this part. It again wants to restore its initial position, and from this position it will go to this position. Again, from this position it will come here, and from this position, such way it will be in motion, and that is that simple harmonic motion. Guys, that is a condition. Here, this particle has gone there. That's why it will try to come back to this point. That is restoring force. Restoring force. That force actually saying this. Okay, and from that restoring force, we could say F proportional to minus x. This line we have to remember. Why we have written minus sign? Guys, x is along this direction, but this force tries to retain the particle to this point. That's why we have called it restoring force. That means this force tries to bring this point, bring this particle to this point. Okay, that's what we said. Restoring force, and the more restoring force, the more displacement. Guys, the more displacement, the more restoring force. Okay, if we increase the x, force will be increased. If we decrease the displacement, force will be less. Guys, and minus sign, because displacement is along this direction, but restoring force to the middle point, so minus sign. Okay, guys, now from this line we could write f equal kx. Here is constant. Okay, just now we got f equal to this, so we can write let me get this. Actually, we need a plus. Guys, here we got f equal to m d squared x dt squared. Just we got f equal to m, and this minus kx, and we could draw this left side, m d squared x d squared plus k x equal to 0. Okay, since m, so we could divide both sides by m. Okay, this squared x dt squared plus k upon m x equal to 0. Guys, here we got this squared x upon dt squared plus k upon m x, and now we could write here omega squared x. Okay, here omega squared x d squared x dt is squared. Okay, omega squared means angular frequency, and here we have taken omega equal to k upon m equal to omega squared. We have taken here k is constant, m is mass of the particle, and so omega is the angular frequency, guys. This is our liquid equation. Okay, guys, for deducting this differential equation of simple harmonic motion, we have to know about the simple harmonic motion condition. This is a restoring force proportional to minus x, and actually what I've written here, velocity, acceleration, F equal to ma, those we have to take in the concept from the Newtonian mechanics. So if you know the Newtonian mechanics, just we know the mechanics, then we can simply draw this differential equation of simple harmonic motion very simply. Guys, for understanding this explanation, we have to remember this figure. Actually, this figure I have drawn from the pendulum. Okay, this is the analogy due to the particle. Okay, since particle is very teeny tiny and we can't see this, and particle is in the medium. Okay, that is invisible, but this pendulum is visible, and we have drawn this analogy. Through this analogy, we understood the particle motion, and due to the motion, we have found differential equation of simple harmonic motion. This and here, omega is angular velocity, x is displacement of the particle. This particle has gone from the medium part to left side or right side x. Okay, and k is constant, m is the mass, and t is the time. Okay, d square x upon dt square plus omega square x is the differential equation of simple harmonic motion. Guys, thanks a lot. Assalamu alaikum.